Understanding the origins of our planet is crucial for grasping the complex processes that have shaped Earth over billions of years. The creation of Earth is not just a story of rocks and minerals. It is a narrative that intertwines with the very fabric of the universe. By exploring how Earth formed, we gain insights into the conditions that foster life and the evolution of our environment. Scientific inquiries into Earth's creation reveal how cosmic events led to the formation of our solar system and the unique characteristics of our planet. This exploration also highlights the significance of Earth's geological history and its impact on climate, ecosystems, and human existence. As we delve into the mysteries of Earth's beginnings, we uncover the interconnectedness of all life in the universe, fostering a deeper appreciation for our home. The Big Bang Theory describes the origin of the universe, which began approximately 13.8 billion years ago. At this monumental moment, all matter and energy were concentrated in an incredibly hot and dense state. Then, a rapid expansion occurred, causing the universe to cool and allowing particles to form. As temperatures decreased, quarks combined to create protons and neutrons, the building blocks of atomic nuclei. Within minutes, these particles fused to form simple elements, primarily hydrogen and helium. Over time, the universe continued to expand and evolve, leading to the formation of stars and galaxies. This process laid the groundwork for the complex structures we observe today. Understanding the Big Bang Theory is crucial as it provides insight into the universe's beginnings and the fundamental forces that shaped everything we know. The formation of stars and galaxies began with the gravitational attraction of matter in the universe. After the Big Bang, the universe was filled with hydrogen and helium gas. Over time, gravity caused these gases to clump together, forming dense regions. As these clumps grew larger, their gravitational pull intensified, attracting even more matter. This process led to the creation of protostars, which are the early stages of star formation. When the temperature and pressure in the core of these protostars became high enough, nuclear fusion ignited, marking the birth of the first stars. Simultaneously, these stars began to group together, forming galaxies. The interplay of gravity and matter not only created stars, but also laid the groundwork for the complex structures we observe in the universe today, shaping the cosmos as we know it. The formation of our solar system began with a vast cloud of gas and dust known as the solar nebula. This cloud, composed primarily of hydrogen and helium, collapsed under its own gravity, leading to a rotating disk. As the nebula contracted, it spun faster, causing the material to flatten into a disk shape. In the center of this disk, the sun formed as temperatures and pressures increased, igniting nuclear fusion. Meanwhile, particles within the disk began to collide and stick together, forming larger bodies called planetesimals. Over millions of years, these planetesimals coalesced to create the planets, including Earth. The process involved complex interactions of gravity, heat, and motion, ultimately giving rise to the diverse celestial bodies we observe today, including asteroids, comets, and the planets that orbit our sun. The Earth formed approximately 4.5 billion years ago through a process known as accretion. This process occurred within the protoplanetary disk, a rotating disk of gas and dust surrounding the young sun. As particles collided and stuck together, they gradually built up larger bodies, eventually leading to the formation of planetesimals. These planetesimals continued to collide and merge, creating a growing mass that would become our planet. The immense gravitational forces at play helped to attract even more material, further contributing to Earth's growth. During this time, the environment was chaotic, with frequent impacts from other celestial bodies. This period of formation set the stage for the Earth we know today, laying the foundation for its geological and atmospheric evolution, which would occur in the following eons. The early Earth was a tumultuous environment characterized by extreme heat and volcanic activity. Formed around 4.5 billion years ago, the planet's surface was molten, with temperatures soaring due to frequent collisions with other celestial bodies. This intense heat led to the formation of a primordial atmosphere, rich in gases like carbon dioxide and water vapor. As the planet cooled, volcanic eruptions played a crucial role in shaping the landscape, releasing gases and forming the first solid crust. This crust was unstable, constantly reshaped by tectonic activity and further volcanic events. The relentless heat and dynamic conditions created a hostile environment. Yet these very processes laid the foundation for the Earth's future development, paving the way for the emergence of water and, ultimately, life itself. Water played a crucial role in the formation of Earth, significantly influencing its development and the emergence of life. One prevailing theory suggests that water arrived on Earth through two primary sources: the outgassing of water vapor from volcanic activity and the delivery of ice-rich comets and asteroids. As the planet cooled, this water vapor condensed, forming oceans that became essential for life. The presence of liquid water allowed for chemical reactions necessary for biological processes, creating a suitable environment for life to thrive. Furthermore, water acted as a stabilizing force, regulating temperatures and supporting diverse ecosystems. Without water, Earth would have remained a barren landscape, devoid of the vibrant life forms that we see today. Understanding water's role is vital to comprehending our planet's history and its potential for sustaining life. The Hadean Eon marks the very beginning of Earth's history, spanning from the formation of the planet about 4.5 billion years ago to around 4 billion years ago. During this chaotic period, Earth was a tumultuous place, characterized by extreme volcanic activity, relentless meteorite bombardment, and intense heat. The surface was molten, and the atmosphere was likely composed of toxic gases, creating an environment hostile to life as we know it. This chaotic setting played a crucial role in shaping the planet's development, influencing the formation of the crust and the early geological features. The Hadean Eon set the stage for subsequent eons as the conditions began to stabilize, allowing for the emergence of water and, eventually, the building blocks of life. Understanding this eon is essential for comprehending Earth's evolution. The formation of the Moon is primarily explained by the giant impact hypothesis. This theory suggests that around 4.5 billion years ago, a Mars-sized body, often referred to as Theia, collided with the early Earth. The impact was so immense that it caused a significant amount of debris to be ejected into orbit around our planet. Over time, this debris began to coalesce due to gravitational forces, eventually forming the Moon. This hypothesis not only explains the Moon's size and composition, but also accounts for its unique orbit. The event was crucial in shaping the Earth-Moon system we see today. The giant impact hypothesis remains the leading explanation for the Moon's origin, providing insights into the violent and dynamic processes that characterized the early solar system. As Earth began to cool, approximately 4 billion years ago, its surface transitioned from a molten state to solid rock. This cooling period was crucial, allowing the outer layer to harden and form a stable crust. During this time, volcanic activity continued, releasing gases that contributed to the nascent atmosphere. Water vapor, carbon dioxide, and nitrogen were among the primary components, creating a thick, toxic atmosphere. As temperatures decreased, the water vapor began to condense, leading to the formation of clouds. Eventually, rain fell, filling low-lying areas and forming the first bodies of water. This process not only shaped the planet's surface, but also set the stage for future life. Understanding this cooling period is essential, as it laid the groundwork for the development of Earth's environment and the eventual emergence of life. As Earth began to cool, water vapor in the atmosphere started to condense, leading to the formation of the first oceans. This process was crucial for shaping the planet's surface. The cooling temperatures allowed water vapor to transition into liquid, filling depressions and basins across the landscape. These primordial oceans were not just bodies of water. They played a vital role in creating a stable environment for future life. The accumulation of water helped regulate the planet's temperature and contributed to the development of a more hospitable atmosphere. Additionally, these early oceans were rich in minerals and nutrients, setting the stage for the emergence of life. Understanding how these oceans formed provides insight into the conditions that fostered life on Earth, highlighting the interconnectedness of geological and biological processes. The origins of life on Earth remain one of the most captivating mysteries in science. Various theories propose that life may have begun in the primordial oceans, where a unique combination of conditions favored its emergence. One prominent theory suggests that simple organic molecules formed in these oceans through chemical reactions, possibly fueled by energy from sunlight, lightning, or hydrothermal vents. These molecules eventually combined to create more complex structures, leading to the first living organisms. The presence of water was crucial, providing a medium for these reactions and a stable environment. Additionally, factors such as temperature, pH, and mineral availability played significant roles in shaping the early biochemical landscape. Understanding these origins not only sheds light on our own existence, but also informs the search for life beyond Earth in similar environments across the universe. Extremophiles are remarkable early life forms that thrived in Earth's harshest environments, such as extreme temperatures, acidity, and salinity. These resilient organisms adapted to conditions that would be inhospitable for most life, showcasing the incredible versatility of life itself. By metabolizing inorganic compounds and utilizing alternative energy sources, extremophiles played a crucial role in shaping the planet's early atmosphere. Their metabolic processes contributed to the production of gases like methane and hydrogen sulfide, which were pivotal in creating a more stable environment. Furthermore, as they proliferated, extremophiles laid the groundwork for more complex life forms by enriching the atmosphere with essential elements. Their existence not only highlights the adaptability of life, but also provides insights into the potential for life beyond Earth in similar extreme conditions. The Great Oxygenation Event, occurring around 2.4 billion years ago, marked a pivotal transformation in Earth's atmosphere. During this time, photosynthetic organisms, primarily cyanobacteria, began to produce oxygen as a byproduct of photosynthesis. This process gradually increased atmospheric oxygen levels, fundamentally altering the planet's environment. Before this event, Earth's atmosphere was rich in methane and ammonia, but as oxygen accumulated, it reacted with these gases, leading to their decline. This oxygenation paved the way for more complex life forms by allowing aerobic respiration, which is far more efficient than anaerobic processes. The rise of oxygen also contributed to the formation of the ozone layer, shielding the planet from harmful ultraviolet radiation. Ultimately, the Great Oxygenation Event set the stage for the diverse ecosystems we see today, enabling the evolution of complex multicellular organisms. The geological timescale is a framework that organizes Earth's history into distinct intervals based on significant geological and biological events. Major events include the formation of the Earth approximately 4.5 billion years ago, followed by the emergence of the first life forms in the oceans. Throughout this timeline, there have been 5 major mass extinctions, including the Permian-Triassic extinction, which wiped out nearly 90% of species. Each extinction event paved the way for new life forms to rise, such as the dinosaurs during the Mesozoic era. The Cenozoic era saw the emergence of mammals and birds after the extinction of the dinosaurs. Understanding this scale helps us comprehend the dynamic processes that have shaped our planet and the evolution of life, highlighting the interconnectedness of geological and biological history. Plate tectonics is a fundamental concept that explains the dynamic nature of Earth's surface. The planet is divided into several large and small tectonic plates that float on the semi-fluid asthenosphere beneath them. These plates constantly move, driven by forces such as mantle convection, slab pull, and ridge push. This movement has shaped Earth's landscape over millions of years, creating mountains, ocean basins, and earthquakes. For instance, the collision of plates can lead to the formation of mountain ranges like the Himalayas, while their separation can create rift valleys. Additionally, plate tectonics plays a crucial role in the carbon cycle and climate regulation, influencing long-term environmental conditions. Understanding plate tectonics is essential for grasping how Earth has evolved and continues to change, affecting both geological and biological processes. Climate change has profoundly influenced Earth's development, intertwining natural cycles with human activities. Throughout history, the planet has undergone significant climate shifts, driven by factors such as volcanic eruptions, solar radiation variations, and ocean currents. These natural cycles have shaped ecosystems and influenced species evolution. However, since the Industrial Revolution, human influence has accelerated climate change, primarily through greenhouse gas emissions from fossil fuel combustion and deforestation. This rapid alteration of the climate system poses risks, including rising sea levels, extreme weather events, and biodiversity loss. The intricate balance between natural processes and anthropogenic impacts highlights the need for sustainable practices. Understanding this relationship is crucial for mitigating future climate risks and ensuring the planet's health. By acknowledging our role, we can work towards a more resilient Earth for generations to come. As we look to the future of Earth, several potential scenarios emerge based on current scientific understanding and environmental challenges. One possibility is a continued rise in global temperatures due to climate change, leading to extreme weather patterns, rising sea levels, and biodiversity loss. Alternatively, advancements in technology and renewable energy could allow humanity to mitigate these effects, fostering a more sustainable coexistence with nature. Another scenario involves the potential for significant geological changes, such as increased volcanic activity or tectonic shifts, reshaping landscapes and ecosystems. Furthermore, the ongoing exploration of space may open new avenues for human habitation beyond Earth, prompting discussions about our responsibilities to both our planet and the cosmos. Ultimately, the future of Earth hinges on our collective choices today, emphasizing the importance of environmental stewardship and scientific innovation. In summary, we have journeyed through the remarkable story of Earth's creation and evolution. Beginning with the Big Bang approximately 13.8 billion years ago, we explored how matter formed and clumped together to create stars and galaxies. The solar system emerged from a rotating disk of gas and dust, leading to Earth's formation around 4.5 billion years ago. We examined the harsh conditions of early Earth, the role of water in supporting life, and the chaotic Hadean eon. The formation of the Moon and the cooling period marked significant milestones, followed by the emergence of oceans and the origins of life. We discussed extremophiles, the Great Oxygenation Event, and the geological timescale, highlighting Earth's dynamic nature and its ongoing evolution, which continues to shape the planet we inhabit today. As we conclude our journey through Earth's remarkable history, it is essential to recognize the intricate tapestry of events that shaped our planet and the universe. Each discovery invites us to delve deeper into the mysteries of our origins and the forces that continue to influence our existence. The story of Earth is not just one of formation and evolution. It is a testament to resilience and adaptation. We stand on a planet rich with history, surrounded by a universe filled with wonders yet to be uncovered. Let this exploration ignite your curiosity and inspire you to seek answers to the questions that linger. Whether through scientific inquiry or personal reflection, the quest for knowledge about our planet and beyond is a journey worth undertaking. Together, let us embrace the adventure of discovery that lies ahead.